maximum price on a strike, and this is it. This is the only thing in the computer in Desert Island to calculate Black-Scholes. And believe me, Black-Scholes is the simplest thing that you can calculate. There are much more complex things you can calculate. Go ahead.
The epsilon is from the standard normal distribution.
Exactly.
So are we the inverse S?
No, the epsilon is standard normal. I need something which spits out things that are standard normally distributed.
Norm is this.
Norm is this. No. Norm is this. How would you use norm as this in the Monte Carlo?
I want the inverse norm as this.
Which is norm sinf. Norm as sinf is the inverse.
Yes, right.
Norm as sinf is the inverse cumulative. Remember, norm as this is your G. Norm as sinf is your G to the minus 1. Let's put it this way. Norm sinf is the inverse cumulative.
Yeah.
Okay, so it takes an interval which is between 0 and 1, cumulative probability, and spits out the sigma. Spits out the sigma. So norm sinf of minus 2.33 is 1%. Norm sinf of 0.5 should be 0. You know, it goes on like this. Norm sinf of 99% is plus 2.3. I'm sorry. Norm sinf of minus 1%. Norm sinf of 1% is minus 250. Norm sinf of 99% is 250. Good point. Etc. Now, a question which also tortures people the first time they do Monte Carlo. Okay? I said I have a 1 year plain vanilla call option. Okay? Have a distribution of the price of this 1 year from now. I say, suppose I don't believe you, and I want to simulate the path of the stock, not in one jump which goes from now to 1 year from now, but in 52 weekly jumps. In 52 weekly jumps, then each week is based on the previous week's price times this formula, but not for 1 year, for 1 week. And I want to essentially, loosely speaking, integrate this, for 1 year. Will I get the same distribution as an endpoint in 1 year, or will I get a different distribution? Well, I'll let you know. I'll get exactly the same distribution. Essentially, it's let's say the fundamental theorem of stochastic calculus, the entire stochastic calculus building block is based on the fact that if I do this and simulate many times to the 1 year horizon, I'll get exactly this kind of distribution as an endpoint.
Central limit theory. Central limit theory.
No, nothing to do with central. But essentially, think of it intuitively. My annualized asset dynamics are made up of weekly asset dynamics. Weeks have to pass for a year to come up. So weekly prices have to close, and then this becomes, for the next week, becomes the starting point, and so on for 52 weeks, until I get my distribution for 1 year. So there is no other way. This is the 1 year distribution. If there wasn't, then this formula would have been wrong. My square root of t rule would have been wrong. Okay? But in this world of so-called static volatility, my square root of t rule, this can directly reproduce that. So if the dynamics of 1 year is the only thing I'm interested in, just for sheer economy, which methodology will I use? This or that? The only thing I'm interested in is the 1 year endpoint.
The first one.
The first one, exactly. When would I use the second one? We discussed an instrument before, where the second one might have been relevant. Remember this funny...
On the price path.
Exactly, this funny barrier option
The
that we
barrier
said.
option.
In that case, I need this because I need the entire price path, and if it was above 16, in our case, then the option is active in the end. If it never reaches 16, then the option is inactive. And you can have also the opposite, which is more fun. You can say the option becomes inactive if the price drops below 90%. So if it goes to 8 and then goes to 12, the option is inactive, you make nothing. If it goes to 9 and then it goes to 12, then you make something. And by the way, last year we said the following. If we're interested in a simulation dealing with the future or at a high confidence level, it is absolutely essential we keep the exponential form. I actually said this a year ago. Okay? Can we make the same statement now about interest rates? It is absolutely essential to keep the exponential form. No. Actually, right now it is absolutely essential that we do not keep the exponential form. Because interest rates have shown that they can change sign. Nothing like a negative price for a stock, can reasonably be assumed, but we have negative price for interest rates right now. So again, when we do interest rates, sometimes we do not use the exponential and we use the direct normal. Basically saying S of t plus sigma I. Whereas this sigma is not in percent, but in the unit of S. So if it's basis points, it's basis points. This is how interest rates work now. Okay, you remember I told you about half the story of Monte Carlo. Yeah. Up to now, we've been talking about the simulation of one thing, and one thing only. In general, we need to simulate, if anything, entire portfolios. Even if I don't have, a very strange payoff dependent on, the relationship of two things, I have a portfolio of 10 shares. I want to simulate a portfolio of 10 shares distribution. Now again, I can be very clever and simulate those 10 shares with the same, because you remember maybe from KPM and Markowitz, if I have a portfolio of 10 shares, I can collapse everything to the attributes of one share and simulate the portfolio. But assume I wasn't as clever as that. Or I had a portfolio with, say, stop losses. Okay? This is a good example. I have a portfolio with stop losses. Meaning, every time a share loses 30% of its value, I just sell it. Okay? Then I absolutely need some kind of, multi-dimensional process to simulate those 10 shares individually. And then see, when my stop losses take effect and what my distribution will look like in the end. I need to perform a simulation of random numbers which are correlated, but then each of them individually is normally distributed. So I can have S1 of t, let's call this S1, yes, S1 and then I can have another parameter which I call S2 of t, and then S3, etc. So I have many parameters, okay? Each one has its own path, its own volatility. The volatility of one is not dependent on the volatility of the other. However, if these are correlated, then if one goes up, the other one has to have an increased chance of going up. Okay? This means then that these two guys are individually normally distributed, but they are not uncorrelated. They are correlated. Okay, this is a little of matrix calculus. Okay, you don't need to know anything about that. The idea is the following. What you should do is the following. It's not necessarily true that if I measure a process, if I measure actual returns of a basket of 10, 15, 20 stocks, okay, and I have a variance, I go through the motions of calculating a variance covariance matrix, just as we did for two things in Excel. Could go through the motions of doing this for 20, 50, 1,000, a million, okay? There is no guarantee that what I'll come up with will indeed be a variance covariance matrix. Okay? Remember, I observe nature, I observe true movements of prices. My true movements of prices, they are not necessarily coming out of a process with stationary volatility and normal distribution. So, one thing, and the other thing, I also have a finite number of observations. If everyone told me that I have an infinite number of observations, I would go back thousands of years for this stock, and actually the distribution is coming out of a stationary volatility with a normal distribution, then I wouldn't have this problem. But effectively, the variance covariance matrix is a way I have to impose order in a chaotic process. If I try to impose too much order, or the process is too chaotic, I can come up with a 3x3 matrix, or a 5x5, or a million by million matrix, which will be calculationally correct, but it will not be a variance covariance matrix. By the way, can you imagine over 3x3 matrix, which is not a variance covariance matrix? Absolutely. Well, it's extreme, you don't find this in calculations. But imagine this matrix. It has 1 on the diagonal, and then -1 everywhere else. -1 everywhere else, what does it say? This says that stock A is always moving opposite to stock B. Okay? This thing is saying that stock A is always moving opposite to stock C. And this thing is saying that stock B is always moving opposite to stock C. Can this ever happen? Absolutely not. So, not every n by n matrix with correct looking entries is a variance covariance matrix. Obviously this is crazy, and when errors get in the way they'll be much more subtle, but this is an example of how you can get an error. So, it's not always easy, always possible even, to have a Monte Carlo, multidimensional Monte Carlo simulation that will reproduce a physical process, okay? Because you may have misspecified the problem. However, and this generally happens when you have many more risk factors than time series data points. So if I watch 2 stocks for 10 days, it's fine. If I watch 100 stocks for 3 years, it's fine. If I watch 100 stocks for 10 days, I could still go through the motions of having variances and covariances, but there's a very good chance that the process I described cannot be simulated. By the way, do you have any idea, a large bank, how many risk factors is playing with individually? 10, 50, 100? How many risk factors are in the risk metrics data set? We're talking about 300,000, roughly. You realize now that the bank that has a portfolio that has 300,000 risk factors, it's impossible to have 300,000 daily observations. Okay, you go about 1,000 years. So, there are clever tricks around that. But, let's go on here, after we get this. Let's go on. A special case. If I only have two things, and I promise you, you'll never be asked to have a Monte Carlo of more than two things, not in this class, then these things have a very, very simple form. Suppose I've got two things. I've got this correlation matrix, and I want to produce a set of random number pairs. Each of them is going to be standard normal, okay? And the two of them as a pair will be linked by the correlation factor R, rho. Okay? What do I start with? What is very easy to get in Excel? Obviously, two sets of random numbers which are normally distributed and are independent of each other. I have one column saying norm sim rand 1,000 times, another column saying norm sim rand 1,000 times. Rand in Excel, every time it's called and every time it's recalculated, it has a different value. So I just have two columns of random numbers, each of which is normally distributed. Each column has random numbers which are normally distributed, and there's no correlation between random numbers. Suppose, for example, I have a third column now. Let me start to produce correlation. I have a third column. Okay, the third column is the sum of the two random numbers. Suddenly, intuitively, don't you see that the third column is going to be correlated to both the first and the second, even if the first and the second themselves are uncorrelated? Because the third has a little bit of the first, a little bit of the second. Generally, we do the following. Okay? We start with a pair of correlated random numbers, of independent random numbers, okay? X1, X2. We set the first of our new distribution, Y1 is our X1. And my Y2 is, I'm sorry, let me do it like this here. I start with Y's. Y's are the independent. And X is what I'm trying to find. And then my X1 will be my Y1. And my X2 is going to be rho Y1 plus square root 1 minus rho squared Y2. This is very, very simple formula. By the way, the square root of 1 minus r squared, rho squared, we see the lot. We've seen it before. Now, one question, very, very basic question. Can you verify that X2 is standard normal? What's the variance of X2? What's the variance of x2? I have the variance of something plus something else. Yeah, go ahead. What?
Sigma of the first one, sigma down.
Yeah, so it's rho squared.
Y1 squared.
The sigma of y1 squared. Sigma of y1 squared.
That's the second term squared.
Plus the second term squared. 1 minus rho squared. Sigma y2 squared plus
2 times the covariance.
2 times rho sigma. The covariance. Okay. What's the covariance of y1, y2? What did we say about y1, y2?
0.
0, exactly, because they're independent. What is variance of y1 by the construction? 1, standard normal. What is variance of y2? Rho squared plus 1 minus rho squared? 1. So it equals 1. So this is standard normal. Left as an exercise might be to just convince yourself that this has a correlation of rho. Or we could also do it in the computer. So, essentially now you have everything you need to run Monte Carlo up to 2 dimensions. Okay? And you will. You will, because this is a very powerful tool. By the way, is there anybody here in a technical field outside finance?
What?
Technical field outside finance, like ship building, ναυπηγική, πολιτικός μηχανικός? Okay, because they're using Monte Carlo. Monte Carlo is not just in finance. Monte Carlo didn't come from finance. It used tons of engineering.
We had a course in υπολογιστικά μαθηματικά.
Yeah, you use tens of applications.
Κάνουμε ένα διαλυματάκι.
Να κάνουμε.